Hello and welcome to Team 1050's project for the SIMIODE 2022 challenge. Our group is Nate Lambert, me, myself, Katie Mccraw, and Nate Welch. We decided to choose problem statement C, which is titled People Ruin Everything. We are from Colorado State University at Fort Collins, Colorado, and our team coach was Matthew Kipper. To get into our project, we will go over the problem statement one more time. Our problem statement for C, like I said, was people ruin everything. And in the main points within that was that we are to look at human and animal presence and how they affect an ecosystem when they are brought together. We were also to look at prey and beginning to lose their anti-predator response over time when part of the ecosystem or all of it is changed, and this is through the change of humans interacting and joining the ecosystem. We are to build a model to look at the trend time over a long period of time when humans are introduced into a system. We did this by a mixture of MATLAB coding and coming up with equations to use that. We will get into that later on though. Humans are to be quickly introduced into the stable ecosystem. That was one of the main points within the problem statement that we had to be considerate of during this building process of our model. And then the research that was based on this problem statement was investigated in the system in urbanized areas. They looked over all of this over 10 periods of time, and we're looking at the interaction between humans and animals in an ecosystem. So we are just here to looking forward into that. Our questions to answer that were given in the problem statement were what happens when humans move out of the system, and would this result in an effective method to restore an ecosystem, or has the damage already been done? We will discuss these questions later on, but right now we will get into our goals and approach method and how we started to build our model. For our goals and approach, you can see here they are within black and blue to help kind of distinguish them. We are to do the impact of behavioral changes over time. That was one of our goals that we set out. And just like the problem statement, we want to predict the long-term implications when prey have an anti-predator response system and when that system is muted. We are to look at the effects of humans when they move in the system as well as when they move out of the system. And then with this, we are then to look at the results of the human migration into that ecosystem and the restoration of that ecosystem, if at all possible, with these human migrating in. Our approach to creating this model is that we use the SIMIODE model as well as the Lotka-Volterra model for prey and predator. These two models we use to help navigate towards our equations based on the assumptions that we created, and we use that within our MATLAB coding to then actually create our model. To explain the models a little further, the SIMIODE model is a mathematical model that looks over the spread of an infectious disease within a population. Within each of the letters in the model itself, SIMIODE, they stand for S if they are susceptible to the disease, E if they are exposed to the disease, I infected by the disease, R who are recovered from the disease, and D the death from the disease. We use this to help look at the interaction of something moving in, exposing a population, and moving out. So that was our basis for using that model. The other model that we helped to use and create our equations with the Lotka-Volterra model. This is a prey consumption rate by a predator proportional consumption rate between the two and the amount of the prey in the environment. So we use this model to help within the stabilizing of predator and prey within a system, as well as when the humans were to then move into that system. Moving on to our assumptions. These are a list of assumptions, and to talk about it a little further, we wanted the change of anti-behavioral and prey due to the human interactions and the analogies to the transmission of an infectious disease. So with this, each interaction between susceptible prey and human can result in the prey changing its behavior over time. Overall, because of this, the behavioral changes occurs and it is persistent. So that was one thing that we wanted to keep within our model and within our assumptions. The other thing that we wanted to keep was the animal interactions and simplify that to what the interactions between predator and prey are. This model does not demonstrate cooperative behavioral between the two, but this assumes the distribution of behavior within prey and predator, as well as with the human population coming in. We wanted to make sure that we muted the anti-predator and prey and the susceptible prey to share a common carrying capacity of the ecosystem. This was shared pool of resources is consistent, and we wanted to keep that within our model. The growth of human population is independent of the animal communities. We wanted to keep those things separate. With that, we can then easily see a population moving into this ecosystem and looking at how it accelerates the saturation point, and as well as an easy way to remove a population from the system in a simplified manner. And I will stay on the screen here for the other assumptions that we made to use our model. Here is our basic form of the equations. We have all of the parameters here on to the left side that you guys can look into. As in talking about the equations themselves, we will go over into the 4 bullet points. The first one being the rate of change in susceptible prey population. With this, our equation is looking at the change of population rate. And we do this by using the susceptible growth rate and subtracting that from the rate that was switched of susceptible prey and the muted anti-predator behaviors that we were seeing. And then with that, we also subtracted all of that through the harvest rate of the susceptible prey. For our next equation, we are looking at the rate of change in muted anti-predator population. In this equation, we are looking at the change of the population rate, and we do this by looking at the rates that switched again from that susceptible prey and the muted anti-predator behavior. We are also subtracting that from that harvest rate, but we are also adding within to that the growth rate of that muted anti-predator behavior and that population coming in. For our third equation, we are looking at the rate of change in predator population. We do this by looking at the change of that population rate, and we do this by the growth rate, payoff rate that would come from the harvest of the susceptible prey. And we add that on to the same thing, but just with the muted anti-predator way. We also take into account here the death rate, as well as the death rate that is caused by humans. And then for our last equation, we are looking at the rate of change in human population. And we do that by looking at just the growth rate of the human population. Moving on to our next slide, this is the simplified versions of our equations, and this would help us to make it easier to look at the rates. and generalizing the rates for them. So with that here, we did take into the account of the generalized attack rate and the conversion factor for different attack rates. So we use that within it to simplify these equations. And I will leave it on this moment here. It is pretty much the same equations that we talked about before, just simplified. We will be now going and talking about our MATLAB methodology. We used MATLAB to create our model, and we used the different built-in functions within MATLAB to help us create this. The main one that we used here was the ODE 45 one, and we used that to help with the predator and prey stabilization, as well as using the introduction of humans into the population. We then used an IVP stabilized formula within that same thing of ODE 45, and that was helped stabilize the humans and animals in the ecosystem. We then use that to then look at the before and after migration of the results of humans entering and leaving the ecosystem. Again, still using the same thing with ODE 45. We then graphed the different results and the rates of changes that we would see, as well as the timeline overall. This is our first graph, and we first did it with migration. In talking about this graph, we can see humans entering into the system and how the stability of the ecosystem was before it crushed, as when the humans was entered into the ecosystem. And with that, because they were entered in, you can see here within the graph that they are working towards a new stability with this added population into the system. In our next graph, we look at the stabilized form of this population. These plots are showing asymptotically growing rate of change, and it does this for each different population in which you can see here. We can see the stability in the domain for each population, and we can see that equilibrium will become unstable down the domain. And we can see that within the different levels that the populations are at. In our final graph, we see that human population was cut down to 0. So this was humans leaving the population and migrating out. We can see that when the ecosystem is changed again, a new equilibrium is to be worked towards amongst the predator and prey population. So this leaves it right now that the population is chaotic and unstable at the moment. In conclusion, from what we can see within those graphs back there, what happens when humans move out of the system, we saw that prey and prey stabilization was no longer achieved, and that all prey with muted anti-predator attributes are dropped out of the system, and it looked like almost immediately. Would this result in an effective method to restore an ecosystem, or has the damage already been done? As we can see, the damage has already been done. The population was stable before the humans came in and had to become stable when the humans entered and became unstable after they left, so leaving them in that chaotic, unstable state. With that, the damage has already been done and they're working to restore a new ecosystem, and it would be different than it was before. Looking back within our model, we know that moving forward, we can use a BVP model within our MATLAB to help accentuate these rates further and creating a more accurate and precise data within that. With that, we can also show the human destabilization that happens within the system. And we also know that we can also look further into the use of literature-derived initial conditions to help us see the destabilization as well as the stabilization in an ecosystem over time. With that, thank you so much for listening to our presentation. The next slide, we will stop here and it will be our resources. Thank you so much for listening in, and I hope you have a great rest of your day.